The National Electrical Code, specifically Article 800.110b, provides exceptions to the requirement of bonding the telecommunications grounding electrode to the home's grounding electrode. This section states that bonding is not required where it is impractical or not feasible to do so. The NEC commentary clarifies that impractical or not feasible includes situations where the distance between the electrodes is excessive or the route for the bonding conductor would require excessive trenching or drilling. When encountering these conditions, it is critical to meticulously document the reasons why bonding was deemed not feasible. These records should be readily available for inspection by the authority having jurisdiction, often referred to as the AHA. This documentation serves as evidence that the decision not to bond was made after careful consideration of the site conditions and in accordance with the allowances provided by the NEC. The Rural Utilities Service, RUS, and its predecessor, the Rural Electrification Administration, REA, also established requirements for grounding and bonding of telecommunications facilities. Generally, these requirements align with the NEC, incorporating similar exceptions for bonding under impractical or infeasible circumstances. Therefore, even under RUS or REA standards, the impracticality exception can be invoked if properly justified and documented. In situations where obstacles exist, such as excessive distance, the need for extensive trenching, or the requirement to bore under driveways, the exemption in Article 800.110b of the NEC can be applicable. It is essential to emphasize the importance of thorough documentation in such cases. The documentation should clearly outline the specific obstacles encountered, the reasons why alternative bonding methods were considered impractical, and the overall justification for invoking the exception. Insurance considerations also play a crucial role in determining whether to invoke the NEC exception. Telecommunications providers should consult with their insurance company to understand the specific requirements for coverage. If the insurance company mandates bonding in all cases, irrespective of obstacles, the provider must adhere to those requirements to maintain coverage. Failure to comply with insurance requirements can result in denied claims in the event of lightning strikes or other electrical damage. To further enhance protection and ensure compliance, several additional recommendations should be considered. Firstly, always use the shortest and most direct route for bonding conductors whenever possible. Minimizing the length of the bonding conductor reduces impedance and improves the effectiveness of the grounding system. Secondly, protect bonding conductors from physical damage and corrosion. Exposed conductors are susceptible to damage from environmental factors, which can compromise their integrity and effectiveness. Thirdly, ensure that all accessible metal parts of the telecommunications system are properly grounded. This includes equipment cabinets, enclosures, and metallic conduits. Fourthly, install surge protection devices to provide an additional layer of protection against lightning strikes and power surges. Surge protection devices divert excess voltage away from sensitive equipment, preventing damage. Furthermore, it is crucial to understand the specific requirements outlined in Article 800 of the National Electrical Code, NEC. Article 800 addresses the grounding and bonding requirements for communication systems, including telephone, cable television, and data networks. Section 800.100 specifically covers the grounding methods for communications systems. It mandates that the grounding electrode for communication systems must be bonded to the building's grounding electrode system. However, as previously discussed, exceptions exist under certain conditions. Article 800.40 pertains to the protection of communications equipment. It requires that communications cables entering a building be protected by a primary protector. This protector is designed to limit the voltage surges that can enter the building through the communications cables. Primary protectors are typically installed at the point where the communications cable enters the building and must be properly grounded to be effective. In addition to the NEC, other relevant standards and guidelines may apply depending on the specific installation and local regulations. These may include standards from organizations such as the Telecommunications Industry Association (TIAR) and the Institute of Electrical and Electronics Engineers (IEE). Compliance with these standards helps to ensure the safety and reliability of the telecommunications system. When assessing the feasibility of bonding, consider the potential impact on other systems and equipment. Improper bonding can sometimes create ground loops, which can cause noise and interference in sensitive electronic equipment. Therefore, it is essential to carefully evaluate the potential consequences of bonding before making a decision. Ground loops occur when multiple paths to ground exist, creating circulating currents that can interfere with signal transmission. To mitigate the risk of ground loops, consider using isolation devices or carefully planning the grounding and bonding layout. Also, remember that local codes and regulations may have additional requirements for grounding and bonding of telecommunications systems. It is important to consult with the local authority having jurisdiction, OJ, to ensure compliance with all applicable codes and regulations. The AHA can provide guidance on specific requirements and interpretations of the NEC. In summary, while the NEC generally requires bonding of the telecommunications grounding electrode to the building's grounding electrode system, exceptions exist when bonding is impractical or not feasible. Proper documentation, consultation with insurance providers, and adherence to relevant standards and local codes are essential when making decisions about grounding and bonding of telecommunications systems. The use of surge protection devices is also highly recommended to provide additional protection against lightning strikes and power surges. Here is a breakdown of some key aspects of grounding and bonding, expanding on the information already provided. Firstly, the purpose of grounding is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. This helps to prevent electrical shock hazards and minimize damage to equipment. Secondly, bonding is the process of connecting all metal parts of an electrical system together to create an equipotential plane. This ensures that all metal parts are at the same voltage, reducing the risk of electrical shock. Thirdly, the grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. These electrodes are used to establish a connection to the earth, providing a path for fault current to flow back to the source. Fourthly, the grounding electrode conductor is the conductor used to connect the grounding electrode to the equipment grounding bus in the electrical panel. This conductor must be sized appropriately to handle the maximum fault current that may occur. Fifthly, the equipment grounding conductor is the conductor used to connect the metal parts of equipment to the equipment grounding bus in the electrical panel. This conductor provides a path for fault current to flow back to the source, protecting against electrical shock hazards. Sixthly, the National Electrical Code, NEC, provides detailed requirements for grounding and bonding of electrical systems. These requirements are designed to ensure the safety and reliability of electrical installations. Seventhly, Article 250 of the NEC covers grounding and bonding requirements for electrical systems. This article provides specific guidelines for selecting and installing grounding electrodes, grounding electrode conductors, and equipment grounding conductors. Eighthly, the authority having jurisdiction, OJ, is responsible for enforcing the NEC and other applicable codes and regulations. It is important to consult with the AHA to ensure compliance with all requirements. Ninthly, proper grounding and bonding are essential for the safety and reliability of electrical systems. Failure to comply with grounding and bonding requirements can result in electrical shock hazards, equipment damage, and fire hazards. Tenthly, regular inspection and maintenance of grounding and bonding systems are necessary to ensure their continued effectiveness. This includes inspecting grounding electrodes for corrosion, checking the tightness of connections, and verifying the continuity of grounding conductors. Now let's consider the situation where the power service is on one side of the house and the telecommunications service is on the opposite side. In such cases, the distance between the power grounding electrode and the telecommunications grounding electrode can be significant. This increased distance can make bonding more challenging and potentially lead to increased impedance in the bonding conductor. In these situations, it is even more critical to carefully evaluate the feasibility of bonding and to document the reasons for any decisions not to bond. The use of surge protection devices becomes even more important when the distance between the grounding electrodes is significant. Surge protection devices can help to mitigate the effects of lightning strikes and power surges, protecting sensitive electronic equipment from damage. Furthermore, consider the potential impact of soil conditions on the effectiveness of grounding electrodes. Soil resistivity can vary significantly depending on the type of soil, moisture content, and temperature. High soil resistivity can reduce the effectiveness of grounding electrodes, making it more difficult to achieve a low impedance connection to the earth. In areas with high soil resistivity, it may be necessary to install multiple grounding electrodes or to use soil enhancement techniques to improve the effectiveness of the grounding system. Soil enhancement techniques may include the use of chemical ground rods or the addition of conductive materials to the soil. Always consult with a qualified electrician or grounding specialist to determine the best approach for your specific situation. The size and type of grounding conductors are also important considerations. Grounding conductors must be sized appropriately to handle the maximum fault current that may occur. The NEC provides specific guidelines for sizing grounding conductors based on the size of the overcurrent protective device. The type of grounding conductor used is also important. Copper conductors are generally preferred for grounding applications due to their low resistance and high conductivity. However, aluminum conductors may also be used in some cases, provided that they are properly sized and installed. When installing grounding conductors, it is important to ensure that they are protected from physical damage and corrosion. Grounding conductors should be routed in a manner that minimizes the risk of damage from impact, abrasion, or exposure to corrosive substances. Also, use appropriate connectors and fittings to ensure a secure and reliable connection. In addition to grounding and bonding, surge protection is an important component of a comprehensive lightning protection system. Surge protection devices are designed to divert excess voltage away from sensitive electronic equipment, preventing damage from lightning strikes and power surges. Surge protection devices are available in a variety of types and sizes, depending on the specific application and the level of protection required. It is important to select surge protection devices that are appropriate for the equipment being protected and to install them in accordance with the manufacturer's instructions. Surge protection devices should be installed at the point where power and communications cables enter the building, as well as at individual equipment locations. In summary, grounding, bonding, and surge protection are all essential components of a comprehensive electrical safety system. Proper grounding and bonding help to prevent electrical shock hazards and minimize damage to equipment, while surge protection devices provide an additional layer of protection against lightning strikes and power surges. Remember to consult with qualified professionals and to adhere to all applicable codes and regulations to ensure the safety and reliability of your electrical systems. The information provided here is intended for general guidance only and should not be considered a substitute for professional advice. Electrical work can be dangerous, and it is important to always follow safe work practices and to consult with qualified professionals when necessary. A final word on documentation: whenever an exception to the NEC or other electrical code is taken, it is critical to document the reasons for the exception. This documentation should include a detailed description of the site conditions, the reasons why bonding or other code requirements were not feasible, and any alternative measures that were taken to ensure safety. The documentation should be kept on file and made available to the authority having jurisdiction upon request. Proper documentation can help to protect against liability in the event of an electrical incident and can demonstrate that reasonable efforts were made to comply with applicable codes and regulations. In addition, it is important to keep abreast of changes to the NEC and other electrical codes. The NEC is updated every 3 years, and changes to the code can impact grounding, bonding, and surge protection requirements. Staying informed about code changes can help to ensure that your electrical systems are up to date and in compliance with current standards.